can come in.
Hey.
If we miss chairs, we can also grab them from the outside or from other offices and so on. Just and I won't be leaving chairs, so just take this one. Okay, let's get started getting into the moon, because this is going to be quite different to what we did before. I hope that I'm not going to be fired for saying this, but there is a big difference. The biggest difference for me with respect to the previous lectures is that polarization is a very new thing to US in the context of measuring, because yeah, somehow it seems like there is this not really official, but sort of distinction that in Europe people more do like classical observations from the ground-based telescopes. They measure polarization and so on and so on. And in US, people more use like space missions with high temporal resolution, fancy wavelengths, and so on. So maybe some of the things are something that you haven't heard a lot in like seminars and colloquia that you attended here. And probably you heard about polarization in your undergrad studies, but you didn't. I mean, this is something that we very often like forget or don't pay so much attention to, etc., etc. So in the spirit of all the other previous starting slides, I started with a picture of Higgs, of course, and then something topical related to today's topic. So now I want to ask you, who knows what this thing on the right-hand side is? I think I saw Momo whispering, so say it aloud.
Poincare sphere.
It's Poincare sphere, exactly. So Poincare was a genius in many aspects. Okay, this is not super ingenious. You can figure this one later. You will see why this is like this. But this is one of the ways to represent the polarized light, right? And so what we did by now and what we studied by now is that we took a look at specific intensity. And this is also something like gradual. This is like the next level of treating the light. We started with basically talking about specific intensity as some sort of number of counts that we receive from unit surface, unit angle, unit time, unit wavelength, etc., etc. And first, we spent a few lectures talking about the spatial dependency, how the intensity varies with X and Y, how it varies in the plane or in the sky, and how we can recover that information using image restoration techniques and adaptive optics and so on. And then last week we talked about the wavelength dependence, and then we talked about the Fabry perils and spectrographs and way to the second in wavelength. And now we want to do another complementary analysis with respect to that. We want to analyze the polarization state of the light. So far we mostly treated the light as a scalar in a way. So I didn't very often use the fact that the electric field is a vector, right? We treated it as a scalar quantity that suffered the diffraction interference and so on and so on. And then we could analyze how it behaves when it goes through a filter or through your aperture or something like that. Okay, but light is a wave and it's actually a transversal wave, so we can probe its polarization. And usually when I give these general talks about, general talks for scientists about spectropolarimetry, I just show this slide and I say you will remember Stokes parameters and how they are defined, and then I just move forward. And now we're going to spend the whole class just trying to figure out what this image here means. So you probably encountered this somewhere. Actually, this is literally copied and pasted for Jose Carlos's book that I wanted to bring here and show to you. But okay, let's say it now. There is this nice, colorful book published in 2003 by Jose Carlos del Toro Iniesta, and the name is Introduction to Spectropolarimetry, and it introduces you to everything that you need to know. Maybe it doesn't contain everything that you need to know, but it's a very good starting point for most of the things. So it starts from basically doing what we are going to do today, like defining quantities and describing the polarization state of the light, and then it moves all the way through physics of spectral light polarization, measuring that polarization, modeling that, and in the end inferring magnetic fields and their orientation. As CU students, and I think also other students who are listening to us remotely, I guess that most of your libraries have that book either physically or you can even download the PDF for free. legally. I mean, you can also do it illegally, but I wouldn't advertise that. So try to do that. If you don't have that, then get in touch with me or your local professors and try to reach it. It's also I think it's a very cheap book and it's worth having for everybody. So we're going to try to understand what's happening here. You are all probably guessing that on the left-hand side, this GIF is showing you an example of elliptically polarized light. On the right-hand side, we have the operational definition of Stokes parameters. So now we are going to try and understand why are they made like that. So, going to the back of the basics, I asked you at the beginning of this course, how many of you would know how to solve this system of equations, which are Maxwell equations in the vacuum? So raise your hands. 1, 2, okay, half of the room at least. Okay, well, yeah, if you need to rearrange, take some gradients and curls of this and rearrange these equations, and you're going to end with Helmholtz equation for E or for B, whatever you prefer, and then you're going to get that basically one of the natural solutions of these are plane waves. Okay. So what I can do in a way, and this is something that is not immediately obvious, is that I can make my electric field. I can always have two electric fields which are completely identical, so have identical wave number, identical velocity, propagate along exactly the same direction, but have different amplitudes and different starting phases, and are parallel to each other, and they're not going to interfere whatsoever. Okay, so here we usually plot one electric field, and always remember that even though we are plotting electric field along one line, what it actually is, it's infinite in x and y, right? This is why it's called monochromatic harmonic plane wave. But in principle, in addition to this x component here, I can have another perpendicular component, and they can propagate without interfering with each other at all. So along this given direction z, for given wave number k and given frequency omega, I have 4 more quantities which completely describe my electromagnetic wave. These are the amplitude of x, amplitude of y, phase of x, phase of y. Okay, cool. In principle, I don't need to treat these two separately, right? Because we always can set our starting phase to 0. So what actually matters and what we need to know is the phase difference between these things here, right? So that's why I have 4, and then I sketch and I say 3 quantities, and these are going to completely describe so-called vectorial state of the light. Why do I call it vectorial state of the light? Because now, contrary to all the previous examples before, we actually are concerned about the orientation of our electric field vector. Now comes a problem, and somebody is going to ask that question for sure. So I'm just going to, say it before that. The natural question that comes now is, okay, why didn't we treat it so far? Like, why didn't we treat the fact that the electric field is a vector when we talked about the diffraction and everything else? And the only answer that I can give you now is that it maybe would be too hard. So have proper treatment of all these things in this famous Born and Wolf book, but if you start reading it, it's a trap, because it's a huge book and very thorough and demands a lot of focus and a lot of devotion. By the way, this is really the Born, the Nobel Prize winner, so the famous Born. Okay, so for now we're just going to assume that our diffraction and our spectral analysis works independently of our polarization analysis. And I sort of announced this before when I said we basically separately do the image restoration, then we let the things go. I mean, we have the image formation, then we let it go through the filter, then we can measure the polarization properties, and we sort of treat all these things separately, even though technically they are not really separate. So this is something that I'm gonna work with now. We're gonna have the quantities that we're interested in are AX, AY, and delta, and now I notice that this delta should actually be small delta. So just when you see small delta, replace it mentally with this one, or vice versa. So we're gonna spend a lot of time today calculating the intensities of the wave. So let's just remind ourselves formally what is the intensity of the wave. I said quite a few times that the intensity of the wave is proportional to the square of the electric field, right? And you sort of already know that because it's also in a way, because the square of the electric field or the magnetic field is proportional to the energy density, and we know that basically intensity needs to be proportional to energy density times the speed of light or something like that. Right? However, keep in mind where that 1/2 comes from. Usually I would say, okay, intensity is 1/2 of the square of the electric field. That 1/2 comes from the fact that for most of these simple cases, in principle, we should find the intensity as some sort of mean intensity over some large temporal interval t, right? And when I really have nice harmonic plane wave, what I should do is I can just square it and take 1/2, and that's it. Because the harmonic plane waves behave as cosines, I square the cosine, I take the mean of that, it's the magical 1/2 where it comes from. So can somebody now tell me, to have this averaging be meaningful, what should the time interval be? Compared to, like, or actually we are looking at the sun, right? We're looking at in optical wavelengths. What's the minimum number here that you would put? What's the period of visible light?
Terahertz.
Terahertz is 10 to the
9?
much harder than that. Sorry.
10 to the 12. Hertz.
A bit more than that. It's roughly 10 to the 15. Yeah. So because you get speed of light, which is 3 times 10 to the 8 divided by the wavelength, which is, let's say, 3 times 10 to the minus 7, it's roughly 10 to the 15 hertz. So to one period is what? Is 10 to the minus 15 seconds. That's a lot, right? So in principle, even if I integrate over 10 to the minus 4 seconds, I'm integrating over a huge number of oscillations. And what we are actually going to see today, and what I'm going to tell you now, and we'll see it during the course, but maybe also to talk about it today, over these 10 to the minus 4 seconds or 10 to the minus 3 seconds that you can, what would you say, Kevin? What's the minimum exposure that we can achieve? 10 to the minus 3, if we're good, right? So even over these 10 to the minus 3 seconds, the actual electromagnetic waves that you're measuring last, whatever that last means, much shorter. And that's going to depend on something that we call coherence time. And that's going to be sort of important for the moments, for our discussion about polarization. So in principle, when we now later realize what coherence time is, and you see here on purpose, I plotted it over the interval of 2 times 10 to the minus 14 seconds, and we have, actually, this is for the light of wavelength 500 nanometers, you have quite a few oscillations here.
Just a comment.
Yeah.
There are people measuring polarization in gamma rays, and their integration time is nanoseconds.
It's nanoseconds.
And they still measure polarization.
Yeah. But gamma rays are then even, their periods are even few orders of magnitude. Yeah. Sure. Cool. So now what we care about is not only what's the intensity of the light, we also care about how an electric field and the phase are distributed. So can you spend, you don't need 5 minutes for this, let's spend 45 seconds of silence to convince ourselves that these 3 waves all have the same intensity. So sorry, obviously I missed the coordinates here. There should be I, J, right? This is EX, EX, EY, EX, EX, EY. Okay, I missed the coordinates. It would be really good if I could now write this. We'll do it some other time. Okay, so in the first one, obviously EX and EY, so maybe you are not confused because the orders are missing. But obviously we have EX and EY, which are in phase and identical and equal to 1, right? Here I have only EX, which is square root of 2. And here I have EX and EY, which both have intensity 1, but EY is lagging by pi-half. Okay, so let's try and plot them. So there's notation missing again, but this makes it more clear here. So I have EX, which is oscillating like this, and then EY has the same amplitude and is completely in the phase, right? And I always like to sketch things so that I keep time fixed, and I plot how the things evolve in space, and then I keep the space fixed, and I make a diagram like this, which describes how things evolve in time, right? So here we have, for 4 colors, we have how the electric field looks like. So we have in the time equals 0, this is EX, this is EY, okay? Then after 1/4 of the period, they're both 0. Then after 1/2 of the period, they're both -1 and -1. And then after 3/4 of the period, they're both 0, right? So it's actually an electric field that is oscillating in a plane 45 degrees between X and Y, right? And has a length square root of 2. So it's basically the same thing as this one, except I just rotated the thing, okay? So they have the same intensity because their electric field is the same. And if you average it, you can do it very, very easily. You have square root of 2, right? Squared, it's 2, and then 1/2 of that is 1, okay? However, with this one is a little bit more tricky. I'll fix these things before I upload them online so you're not confused anymore. Now we have EX and EY that are not in phase, but they have a phase difference of pi-half, okay? So now if you sketch that, in the moment, so for Z equals 0 and T equals 0, your EX is going to be 1, your EY is going to be something complex without the real components, so it's going to be 0. And then as you sketch it for these different moments in time, you're going to see that basically your electric field vector is all the time equal to 1, and it rotates like this. And this is what we call left-handed circularly polarized wave. Okay? And now, because the electric field is always 1, it doesn't oscillate between maximum and minimum values, it just changes the orientation. My intensity is just going to be E squared without 1/2. So it's going to be 1 again. So all these 3 have the same intensity, but they obviously have different properties. And the important thing for us is that these different properties are signature of some physical processes there. And hopefully at the end of the lecture, we'll have time just to look at a few different examples to see what kind of physical processes leave the imprint with polarization, and we can measure them later. Okay, so now this part is a little bit clearer. Obviously, I can have a lot of intermediate solutions for this. So I can have EX and EY, which are not exactly the same, and then they have some non-pi phase difference between them. And in that case, we would call that elliptic polarization. And here is a particularly convenient example of elliptic polarization, where obviously EX is bigger than EY, but phase difference is pi-half. If I change the phase difference to be something else, this ellipse would be rotated around the beginning of the coordinate system. Okay. Cool. Yes.
So if you have elliptical polarization, the intensity also varies with time, with the period.
It does, but the point is that we can, and I'm going to stress it a few times today, the intensity varies with time, but we are always measuring average intensity. So because of the fact that intensity varies with time with the same frequency as the electric fields oscillate, there is no way that we can ever measure that for optical radiation.
If you follow one period, it's like the number of photons increasing and then decreasing?
No. Okay, that's a very good question. I'll come to that in a little bit. So try to remember that and ask me again if I don't answer it. Because equating photons and electric fields is very hard. Okay. So then we can use something, and maybe you remember this from your undergrad, something called Jones formalism. And Jones formalism distills these expressions, which are in this situation technically wrong, but okay, we are over that now, distills these equations to their essence, which means it just writes EX and EY as their complex amplitudes, which means I can forget about the term e to the I of kz minus omega t, because they all have it. I just have the amplitude times e to the I phase. And then I can write my complete electric field vector as these vectors here, which are basically just two complex numbers, right? So this was the way to write our first example, which was Ex and Ey are same and they are in the phase, so I have 1, 1. The second one was Ex is square root of 2, Ey is 0, so I have square root of 2, 0. And here I finally have Ex and Ey, which are the same, but Ey is lagging by pi half. Okay, so I'm gonna put this e to the I pi half, which is I, so it's gonna look like this. And this is pretty cool. We're not gonna use Jones formalism for insular physics because Jones formalism only applies to plane monochromatic blah 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 ideal waves, which we are not detecting. But it's good because it teaches us to stop caring about the things that we can't measure. Okay, so we can't measure these, how the intensity is oscillating with the period of the wave. We can only average over much higher intervals. So we sort of just go to the important things, which are the amplitudes and the phase difference. Cool. So now comes the question, and now you can take a few minutes to try to think about how to produce a circularly polarized wave. So you have some wave, you can make it any way you like, which is not,
in the Jones formalism?
In the Jones. Well, you can also just not use any formalism. You can just tell me you need this component, and this is what's going to happen. But you can also write it in Jones formalism if it's easier for you. So let's say you have monochromatic harmonic plane wave, which is oscillating only along Ex. How do you turn it into circularly polarized wave? What do you need for that? And don't think about unpolarized waves, because we still can't actually describe these with Jones formulas. Because also, as Francisco told me this morning, obviously it made him sick because he didn't appear today. The unpolarized waves technically don't exist, right? So does anybody have an idea, like what kind of components do I need? What do I need to do to the distribution?
You need two electric field components, obviously.
Okay, I need two electric field components. That's a good start. What else do I need?
They should have same amplitude.
Okay, yes.
They should be off by pi by 2.
Okay, so what kind of devices would I need for that? Have you heard of devices like that?
Oh,
Change the speed of light.
Change the speed of light, yeah.
I need a retarder.
But you can do that, yeah. Exactly, you need something called retarder or quarter wave plate in this case. So the solution is something like this. Of course, I told you not to think about unpolarized light, but you can put anything that you want here on the entrance. So the entrance is here on the right hand side. And for the moment, just imagine that here we have something. Even any linearly polarized wave will do, as long as it's not really perpendicular to this orange line here. So this orange line here indicates the direction that this linear polarizer here is transmitted. So we can make devices which are called linear polarizers, which only allow the electric field, which only transmit the electric field along specified direction. Okay. So what this linear polarizer is going to do here is it's going to project any kind of the electric field that is entering onto its, let's call it, transmission axis. Okay? So what comes out of there is a linearly polarized wave. So now we pay attention to the middle part here, is a linearly polarized wave which has same components along X and Y. And then we have a particularly useful component here that is called quarter wave plate, which has a very convenient and peculiar property that it induces some phase lag in one component but not in the other one. Actually, what I think is happening is that it induces the lag in both of the components, just not in the same amount. So what you actually get is some prescribed difference, which depends on the thickness of this quantity here. So when they go out, one is going to lag by pi half with respect to the other one, and you're going to get a circularly polarized wave. So to make a circularly polarized wave, you need at least two components. You need a polarizer that's going to give you the same amount of X and Y, and then you need a quarter wave plate, and it's called quarter wave because it retards by pi half, and pi half corresponds to the quarter of the full wavelength, of the full period. Cool. So, so yeah, this is just a summary of what I said now, and in principle, it is very nice to basically what you need to do is you need to change the amplitude by pi half, and in a way you need to go from this vector. So now I'm just discussing this this second part. So this part here. So we entered with 1 and 1 with same EX and C and EY, and we turned it into 1 and I, which is in our Jones notation the spherical, sorry, the circularly polarized light. And one of the ways to do it is to introduce Jones matrices, which are now basically operators acting on these Jones vectors, and which illustrate the effect of optical elements. So in this notation, this 1, 0, 0, I would be a Jones matrix of a quarter wave plate that has so-called slow axis oriented along Y. And this way you can make a lot of interesting things. Right, so this is a very important thing to remember because we actually use these instruments, and I'm going to show you at the end how you can use exactly these two things and just rotate them to measure the Stokes vector that is coming from the sun. Cool. So what we got so far? What's the difference with the studies that we talked about now? So first, light is the vector. In the context, the electric field is the vector. And three numbers to characterize that. Right? At least for the simple harmonic plane wave, right? And then this combination of phases and electric fields, we didn't see yet why, we'll see maybe at the end why, hopefully, carries some physical information that is important for us. Like if I'm looking at a sunspot and I see circular polarization, which is positive or negative, it implies something, right? If I look at the prominence and I see linear polarization only along this side, and then maybe I see it also in other component, then it also tells me something, right? So it's in our interest to measure the amount of polarization in the light. But for that, we're going to change the formalism because it's going to become clear soon why. So we're going to introduce so-called Stokes parameters. And this is finally their definition for the harmonic monochromatic plane wave. Okay? And basically these A are now the amplitudes. And you can define them just through the amplitudes of X and Y and the phase difference in between. And the expressions are fairly simple. And obviously, since I can define 4 different quantities, and they depend on 3 values, something there is redundant, right? And actually for this, you can show, if you just play around, you just need to substitute things, you will get that square of the intensity is equal to the sums of these Q, U, and V Stokes components. And, but we know that in nature it's not like that. So this is only true for very idealized cases, for our idealized waves, which we're going to see now we can't really measure because they don't really exist. We would have to measure on super small time scales and super small wavelength intervals to really obtain that. But yeah, basically this is what I, Q, U, and V are. And now what we try to do is we try to measure these together with their spatial and their wavelength variation. Okay? So cool, let's now calculate IQUV for some example. Okay? So let's take this example here where EX and EY are the same and they are in the phase. If you calculate I, it's going to be what? Well, 1/2 of AX squared plus AY squared, it's 1. Q is AX squared minus AY squared, so it's 0. U is 2 times 1/2 times 2 times AX, AY cosine of the phase difference, which is 0, so it's 1, and V is 0. And this already tells you some physical interpretation of Stokes Stokes U. Our wave was oscillating at 45 degrees to X, and its U component was maximum, the other two were 0. So we're going to see now how we can actually define Stokes parameters through basically measurement, and that's why they so interesting. In a way, these definitions we just saw connects to the way that we are measuring them, or we can operationally define them. Okay, so one example now, let's take a completely different example and try to measure the Stokes parameters, or in this case, linear polarization of a wave like this. Okay, so I have AX, which is 2, AY, which is 1. They are in phase. And now I'm letting them go through forget the blue part by now. I'm letting them go through a polarizer that only transmits X component. What goes through? Well, obviously the black line will go through, AX. And what I measure in that case is 1/2 of AX squared is 2. If I do the same for the perpendicular orientation, I'm going to get 1/2 of AY squared, which is 1/2. So what I measure in this case is, in total intensity, is actually going to turn out to be sum of these two measurements. It's going to be equal to 2.5. Q is going to be the difference of these two measurements. It's going to be 1.5. And actually, when you substitute these expressions here, you're going to get the same things. So without looking, can somebody tell me, since this is still nice, harmonic, plane parallel, blah, blah, blah wave, what has to be the value of U? So even without any definitions. So is there any amount of circular polarization in this system? No, because there is no phase difference. It's a monochromatic ideal plane wave. So it has to be totally polarized. I has to be Q plus U plus V. So if I is 2.5 and Q is 1.5, U has to be 1. Well, is it really 1? It's squared. So it's I squared is 4. Sorry, I squared is 6.25. Q squared is 2.25. So U squared is going to be 4. So it's going to be 2, right? So let's go back to the definition here. U is 1/2. 2 times 2 is 4 times 1 is 1. There is no phase difference, so it's 1. So it's 1/2 of 4 is 2. So it checks out, right? And now you could repeat the exercise by putting the polarizer at 45 degrees and minus 45 degrees, and difference of these two measurements would be your Stokes U. Okay. So now a bit more complicated situation. Now we need to measure the circular polarization of the wave. I'm sorry for these sketches, but now these curly lines illustrate the wave plate, and the straight lines illustrate the linear polarized. So what do I have here? I have here a wave where EX and EY are the same, right? But EY has some phase shift. Okay, so I wrote it again in the Jones formalism because for these kind of waves it's the simplest, right? So now this, don't pay attention to blue once again. This one is going to add phase to EX as well. Okay, so when I add the phase, when I add pi-half to the EX, then EX and EY are again in the phase, right? And then they are basically creating a linearly polarized wave at 45 degrees with EX. And then what I'm putting here, I'm putting a polarizer that transmits exactly at that angle, and what goes out is basically full intensity, right? There is no loss of the intensity in this system. But now if I just rotate my quarter wave plate, what's going to happen? Well, my EX is going to be unmodified. My EY is now going to be shifted not by pi, not by pi-half, by full pi, which means it's basically going to change the sign. It's going to be polarized like this. So pay attention to the blue sketch now. It's going to be polarized like this. So it's going to be polarized exactly perpendicular to this linear polarizer. So 0 is going to go out. So just by rotating this quarter wave plate here, I can measure the circular polarization of my system. And in this case, it's actually minus 1. Okay? And these signs, whether it's -1 or 1, it changes a lot how you define your phase difference and what is right, what is left, etc., etc. So maybe I even made some sign error here, but it doesn't matter so much. What matters is the process. So now, in a way, we understand this second part of the following sketch. Okay. So I, Q, U, and V are basically all some sorts of intensities. Okay, and these would be their operational or measured definitions. So I, and here there is actually missing part, because I is equal vertical plus horizontal, but it's also equal 45 degrees minus 45 degrees, and it's also equal right-handed plus left-handed. Okay. Q tells you basically the difference in the polarization, in the linear polarization, between the measurements when you orient your linear polarizer vertically and horizontally. However, since that's not unique, it's not enough to describe the linear polarization state of your wave, then you also need Stokes U, which is going to be the difference between the positions of 45 degrees and minus 45 degrees of your linear polarizer. And finally, to measure Stokes V, you need a quarter wave plate, and you need to rotate the quarter wave plate to obtain left or right-handed to get the. Well, actually, you can rotate either the quarter wave plate or the linear polarizer to get these two situations and to infer the quantity of to infer the amount of circular polarization. What was always unclear to me was this cosine delta appearing here. So when I saw this first time, I was like, wow, how can it be? What is the phase doing in the linear polarization? But then when you think about it, in a way, it's this cosine fixes that, right? If there is no phase difference, this cosine here is maximum, this sine is minimum. So it's all described by the linear polarization. If the delta is, for example, pi half, this cosine goes to 0, this here goes to maximum. So in a way, circular and Stokes U and Stokes V both demand presence of oscillation in both your axes, but then for small phase differences, you basically have linear polarization. For large phase differences, you have circular polarization. Okay? Okay.
That's just the choice of the coordinate.
That's just
why.
Huh?
Because you've chosen U.
Yeah, of course. Yeah. No, but I mean, now when we are all used to the fact that this is like this, it was always sort of confusing to me. Why? What does this imply? Cool. So we understand this in a way, but not really, because you have probably heard many times by now that the light that we measure is not 100% polarized. It's actually very weakly polarized. Do you know, like, typical polarization degrees in the sun? Come on, you know something. In the optical domain, like in the sunspots, what is the degree of polarization?
5% maybe.
Okay, more than that, but what would you say is the upper limit? Okay, it's maybe like 30–40% at most, right? And that's very peculiar. It's really high level. Okay, 5% you can even see like in plage and the quiet sun. So what's today we talked about hazel, we talked about prominence and filaments. What are the amounts of polarization there? Few percent, maybe a few fractions of percent, something like that. Sometimes we can even measure very low degrees of polarization, like less than 0.1%, if we really collect a lot of photons and average over huge regions and so on and so on. So it's usually very weak. And the reason why we do that is that we are definitely not seeing nice harmonic monochromatic plane waves. Instead, what we are measuring is some mess, where in principle, if that mess was complete mess, we wouldn't measure any polarization whatsoever. because things would oscillate with different wavelengths, different orientations, different durations, different phases, and everything except the Stokes I would cancel. Okay. And we talked about coherent and incoherent sources before, and I was a bit stressed by this, so I even had some dreams tonight about like what's coherent, what's incoherent. So it's actually very hard to think about this, right? We somehow imply that things are coherent, but when we talked about the diffraction, we said that basically, okay, if I have one atom emitting and the other atom not far away from it emitting, they're going to be incoherent. So in a way, when we analyze diffraction, we are looking at the diffraction of all the wavefronts coming from the sun are incoherent. Like it's almost as if one emission process would yield only one coherent wavefront, right? And I said this like rule of thumb: if I have coherent sources, then I can add their electric fields. But if I have the incoherent sources, then I have to add their intensities. And now a natural question is, why is it so? Because Maxwell's equations are linear in their nature, so we should just be able to add electric fields as much as we want. And the answer is yes, of course you can, but the question is, what are you measuring, right? And the difference there is the following one. When you look at coherent sources, then your measurement allows this, either you measure, which is rare, on the scales which are shorter than the coherent time scale, or you simply look at the phenomena where this coherency can show itself, right? But very often, like when we look at light bulbs, when we look at the sun, all the things cancel each other. And now we're going to look at the example that shows that really nice. So one way to look at the coherence and to maybe understand it is to do the following exercise. What I did here is I plotting the electric field for two electromagnetic waves that have very, very similar wavelengths. So one here has wavelength 500 nanometers, the other one has 505 nanometers, so they differ by 1%. And I'm again plotting them on the time scale of few periods, right? And you see here that these two electromagnetic waves are almost ideally superimposing. Like they're basically interfering constructively. So what kind of sorcery is this? How can they interfere constructively? What's the trick? What I'm hiding from you here? What am I hiding from you?
Later on, they're going to destruct.
Later on, they're going to destructively interfere. So here, what I have is that if I add them together, so I can share with you later the Jupyter notebook for this. It's very simple. So when you add this, you square this electric field, you calculate the mean value, you're going to get 2 for intensity, for the basically mean intensity, the thing that we measure. Intensity of each individual wave, in this case, is 0.5, which is basically ideal interference here. Like they behave as two coherent waves, but only if I add them on this small interval here. Now is like, let's see how much, at least an order factor of 20 or something like that more waves. And now you actually can't see the oscillations of these two individual waves. They are hidden here in this orange continuum. But now their superposition exhibits oscillations. Okay, so now at some moment the waves are interfering constructively. In some other periods the waves are interfering destructively. And if now I average the intensity, I'm going to get 1, while the individual intensities of these two waves are again 1/2. So in this whole chunk, they are behaving incoherent. But keep in mind that still, even on these chunks when they are canceling, they are still coherent, right? They're just destructively interfering. So coherency doesn't imply that things have to interfere. It just says, okay, I can add them and the interference phenomena will exhibit, okay? And that's why when you do the interference experiments, for example, for really large path differences of the waves, you won't see interference anymore. Okay, and it has something to do with the property of your source, which is so-called temporal coherence. And the temporal coherence basically tells you something about the duration of these electromagnetic waves. Okay. So what would be, let's now think a little bit, when I threw out some ideas, let's think a little bit, and now we can already discuss for some time, like we tend to sometimes. What would really be an unpolarized wave? How do you manage an unpolarized wave? And this is not a trick question, so I'll explain later why I said this joke that there is no such thing as unpolarized wave. But what would you, let's say that we have agreed that there is something that we call unpolarized wave, and for us that would mean that it's a wave whose Q, U, and V are all zero. What would that be?
The light goes off in all directions and not just a single phase. The light, by light, I mean the amplitude of the electric field goes in all directions.
Goes in all directions. Yes, but since the electric field is vector, and we are still focused on one direction, if I have many different directions of the electric field and I add them, they're going to add to zero. So I need something more than that.
The wave whose polarization is varying on a time scale much shorter than our exposure.
That's a very good answer. So let's keep that answer and let's discuss it later in the context. This is a very good answer. So for some magical reason, the orientation of the electric field and the phase difference between X and Y is changing on so small scales that when we measure it, it's all jumbled up and it all averages. That's a very good one. Does anybody have any other ideas? So before I taught optical, yes, Kevin.
Also, if Q and U are both zero, and there's some intensity, right? I mean, you should have the same amplitude. Two polarized beams, two components of the polarization in the four different directions that are all the same.
Yeah, but that's very hard to make, right?
Well, it gives you unpolarized light by
Yeah,
that definition.
by the definition, yeah.
Right, so to get exactly that.
Yeah, but how do we make it, right? Like what we need to have. So before I taught optics in the last semester, I had completely wrong idea. I thought that if you simply say take electromagnetic waves and give them all random orientations and random phases, they're going to be unpolarized. But that's wrong because they're going to be zero. Because we have random orientations and phases, it'll have a huge number, averages to zero, and I actually tried it this morning and it's true. The higher number of them you add, the closer to zero you get. So that doesn't work, you need something else. Yes, Mama?
You need no correlation between two EX and UY.
What do you mean by that?
Well, because all the Stokes vectors are just the products of of the coherence matrix, right? They're like EX, EY. So if you don't have any correlation between them when you time average them, they're going to go to zero.
Aha, so you need to have no correlation when you time average them. That's exactly the thing behind. These things need to change, and this basically connects to Jonathan's argument, is that these things need to change on much smaller scales than what your measurement time is. So that when you add that, everything except the raw intensity is going to cancel out. So one of the ways to think about it is, but this would be very much harder to illustrate, is that maybe we are looking at the ensemble of the waves which don't all have exactly the same wavelength, right? So when I look at them at big intervals, they're gonna, sometimes cancel, sometimes amplify each other, and on average, they're gonna be incoherent. But one way that you can think about these is you can say, okay, what we are actually measuring are some things that behave as nice monochromatic plane waves, with the exception that they don't last infinitely. They have limited temporal duration, and that temporal duration is again much shorter than our integration time. So what I'm measuring is, I'm measuring maybe one packet which is polarized with some Q and U. But then what I'm actually measuring is 10,000, 100,000, million, billion these packets, all independent because my integration time is many orders of magnitude bigger than their individual durations. So then their intensities just add while their polarizations cancel. And in a way, and now comes the answer to Neeraj's question, in a way we could think of these packages as photons. So when you talk, you can try and explain this, you know, electromagnetic theory of absorption and emission of the atoms. There is actually, I can recommend you this very nice thin book called Introduction to Modern Optics by Fowles. And there is a very nice argument at the end how, you know, transition between two quantum states has some duration and how we can model the behavior of our electron during that period and how that will give rise to various types of electromagnetic waves. And actually the duration of that transition corresponds to some typical length of your wave packet. And these durations correspond to basically what we call coherence time of our emission. And in Jose Carlos's book, I saw that it's maybe 10 to the minus 13 for the optical lights and for typical emittance and so on. So it's basically what you see, one emission process yields like, of course, this is very hand-waving argument and explanation, like photons are photons, right? But if you were to sort of try to model it as an electromagnetic wave, one emission process would yield maybe 100 oscillations, which is actually a very small number. And then when we integrate for 10 to the minus 3 seconds, or 10 to the minus 2 seconds, or 10 to the minus 4 seconds, we capture many of these individual emissions, which almost don't overlap at all, right? And I'm basically measuring individual photons, which are all individually completely polarized, but then their polarizations cancel. And when we talk later about photons and their polarization, and specifically about Zeeman effect, we're actually going to see, and I'm just going to give you a teaser at the end of the class, what happens and how the photons are actually always 100% polarized. And it's just that usually cancels, but there are some phenomena which can break them. So in a way, we are measuring this. So now our definition of IQ, U, and V, and there are, so the averaging now corresponds to this 1/2 that we had before. So this is some temporal average of these quantities, right? And in principle, it's not only delta, it's also x and y that are time dependent, right? And now if you just put some random quantities for ex, ey, and delta, and you average this over a huge ensemble, it's pretty obvious that these things are going to add to 0 and that this thing is only going to increase, right? Because ex, ax, and ay always have to be positive. So I'm always, as I'm increasing the number of packets, I'm always adding the intensity. While here, this is sometimes positive, sometimes negative. This is sometimes positive, sometimes negative. This has random factor, and so on and so on. Okay. So one way to think about this is to think about the fact that we have this mixture of photons, and then if our physical process for some reason breaks this balance in the number of photons, it produces a little bit more left-hand polarized one than the right-hand polarized one. It produces a little bit more linearly polarized along this direction, linearly polarized along this direction. We can measure that and we can detect it. Okay? So I call on purpose these photons waves, but we can also call them photons. There is no problem there. So Stokes formalism now works with intensities, and what we do basically is we just linearly add properties of these individual wave packets, and everything is linearly acting on intensities. So before we had sort of linear theory, but acting on the electric fields, now we work on the intensity. And sort of justification for that is that the wave periods are ridiculously small, like 10 to the minus 15. Coherence times are still ridiculously small, like 10 to the minus 13, 10 to the minus 10, and so on and so on. And our integration times are much larger than both of these, right? So we always see incoherent. Yes.
And the number of events, packets we're collecting.
It's huge.
Well, is small, right? If it's
It's
13
yes.
possible, intervals in that 1 millisecond exposure, and we're only detecting 1,000 or 10,000
Yeah.
or whatever, 100,000 events means they're largely.
They're sparse.
They're
so to speak.
sparsely.
Yeah. It's I mean it's small, so it keeps us in linear regime.
Right.
Yeah, but when I said it's large, I meant it's large enough so that unless there is a physical process underneath, it will always statistically cancel to no polarization. Right. Okay. Cool. So these are some of the nice. This is something that you probably already intuitively feel, but this is just a refresher. A few typical completely polarized waves, right? So okay. Natural light is obviously not completely polarized, right? But this would be completely unpolarized waves. So we have some intensity, but all the other components are zero. And now this is something that we saw by now, right? That the light that is linearly polarized along x is going to be 1 and 1. Along y is going to be 1 and -1. And some of the discrepancies between me and the book come from the fact how I oriented my x and y. I oriented z to go toward us, and I wanted to have the correct notation. So my x was like this, and my y was like this. But this is just a matter of science, and you always need to ask your telescope operator how they define q, u, and v anyway. So there is no loss of information here. Okay, cool. So now let's just talk a little bit how we can measure the Stokes vector of the observations. So to do that, we are going to look at these two typical instruments that we used before in Jones formalism, the linear polarizer and the quarter wave plate, or actually any retarder, because the quarter wave plate has specific thickness or whatever property to induce exactly pi half. You can make it to introduce any retardance that you want. So what we're going to do is we're just going to model the electric field and its behavior, and then we're going to see how application of these two instruments jointly affects what we measure, right? And if you only have Ex and Ey and they're entering the linear polarizer, what you get through it are some new components which are modified by these factors cosine theta and sine theta. So you can sketch this on your own and convince yourself of that. And then if we were to use the quarter wave plate, right? So it wouldn't absorb anything. It wouldn't modify the amplitude of your EXEY, but it would introduce some phase change. Right? So now we can use these to see how the measured intensity, so this is intensity. So now what I'm showing you here is the intensity after your original Stokes vector passes through the system of linear polarizer, which is inclined with the angle theta, and the retarder with retardance delta. Okay, and when I substitute that there, my measured intensity of the light is going to be square of my electric field. Okay, so in that case, when I substitute these quantities in, I get something like this. And then it actually turns out that the real components of I can express this as taking the real components of this, and then it's gonna turn out that this is basically a linear combination of I, Q, U, and V of my initial wave, my initial light. So I don't understand you to now connect this derivation immediately, but this is what it turns out. So when I have a system which has a linear polarizer and the retarder, and I orient them in some way, what's going to happen is that I'm going to get some linear combination of I, Q, U, and V. So now I gave you already the answer, but now you're probably guessing that what we actually measure is this quantity here on the left, while our unknowns, when we look at the sun, are I, Q, U, and V. So what I can do is I can change these two angles to get many different measurements in order to retrieve my values of the Stokes parameter. And that is what we call modulation. So you have probably heard the term modulation, and we're going to just now very briefly say what is temporal and what is spatial modulation, and Valentin is going to tell you much more about that on Thursday, and Francisco on Friday, and on next Tuesday. But basically the idea is the following. If I had 4 different values of theta and delta that I know, I will have 4 different measurements, and some values for these coefficients here, which I know, and I can derive 4 unknowns, which are IQ, UV. I can even make more than 4 measurements. I can make 6, or I can randomly modulate, as some people suggested, to have a huge number of these, and to and then in that case we get overdetermined system, where now we are basically getting IQ, U, and V as the best fit, which in principle could yield less sensitivity to some things. So, in practice, what you would usually do is you would combine this thing in some way, and one thing that you can do is you can take time to change these orientations, or you could use something which is called polarized beam splitter, where you immediately divide the things into states of perpendicular polarization, and then you apply these quarter wave plates later. And to do that, we can either project different modulations in time, so I can make successive images of different modulation states, or I can project them at different cameras or different chunks of my camera, and that is what we call spatial modulation. And now it would be technical to go into advantages and disadvantages, and I think that Valentin will maybe cover that in more detail, and Francisco, of course, but I mean, both of these have some advantages and disadvantages because they are sensitive to your camera characteristics and to what happens in the real sun, and there are some very interesting things called like seeing induced polarization, etc., etc. But in principle, the idea here is that we get different realizations of the measured intensity. So we are never measuring Stokes parameters directly. We always measure linear combinations of Stokes parameters and infer the Stokes parameters from that.
Ivan?
Yes.
So in this case, what would be the advantage of getting into the overlap case? If I was going to go from a square matrix to a non-square matrix, what would be the advantage here?
I think that in practice, you don't really know this with huge precision. Like this is also obtained through some calibration. So I would say that you are less sensitive to calibration errors. But I don't know. Andres and Kevin, what do you say?
Yeah, sometimes it's related with efficiency. So if you measure only 4 times, then you can measure the Stokes parameter with some efficiency, so some signal to noise ratio. And if you measure more times, you can increase this efficiency for QU and V. That's probably the single point of that. Otherwise, if you have 4 linear combinations, that's enough. It might be that the linear combinations are not strictly independent. And then you probably need more than 4. So, I mean, you can have some alignment on the 4 equations.
But do we have that here or not?
Well, you can tune the angles so that you end up with sufficiently linearly independent measurements.
You need to choose your angles.
Yeah, you need to choose.
Not any 4 measurements will do, right? Yeah. If I choose a delta such that I'm insensitive to U and V, right?
You only have 2 parameters to play, and you need 4 different measurements. So, I mean, there's not much options.
So in practice, you would normally try to get the angles and the displacement so that you can cancel some of the terms there.
That was the original way of doing that. So the original way was to measure I plus Q, and then you make the rest
and now you
0.
beam split it and get 2 of them for H and so on.
But now people, I think, they measure only 4 times in 4 different quantities there.
Right, there's different combinations to balance the contribution from the IQ, U, and V, so that like you're saying, the signal to noise, the amount of signal you get from your V signal is equal to the amount in the Q and the U, so you can choose.
We'll try to do it next week. I'm trying to obtain some exercises where we would actually make our own scheme, and we would be able to infer something called modulation matrix, and then from that modulation matrix you get the numbers which are basically your efficiencies. Because it's not super obvious from here, but if you make, for example, if you were to make 4 measurements, as you suggested, in the classical way, each of them, you would accumulate enough photons to basically measure I with all 4 measurements, but you would get like, you would get much less photons to determine each of the other ones, in a way. So then, I think if you use 6, then you somehow balance it in a better way, but we would really have to plot this. And I think if Valentin was here, he would probably make fun of us for not knowing this, but okay, we can keep that in mind and ask him on Thursday. Okay. Yeah. Okay, so.
Just a single comment. Mathematically, this is equivalent, but since you are dealing with quantities that are noisy,
Yeah, I think
then
that's.
you have to take into account the error propagation there. And then.
So like then you're getting into the words maybe like more averaging.
No, so the measurements you make are noisy.
Yeah.
So you're inverting a system that is noisy. So and for if you make 4 measurements, the 4 measurements will contribute to I, but not the same quantity to Q, U, and V. So the error propagation is different for the 4 Stokes parameters.
Yeah, okay.
So there is some freedom on how to choose this modulation matrix so that you find almost the same efficiency in the error propagation for Q, U, and V, something like that. Okay. You might end up with a modulation matrix that you assume that you're measuring Q, U, and V, but the error statistics for V is horrible.
Okay, and then one thing connected to that, we won't talk about this a lot today, are the so-called Mueller matrices, which are now in a way equivalent to Jones matrices that we had before. So I can depict the changes in my Stokes vector when it interacts with a linear polarizer or a retarder or anything else through this 4x4 matrix here. And there is now much more things happening behind. They need to satisfy certain conditions, and like simply from the arguments of what they do to the electric fields and so on, you can write down the Mueller matrices for linear polarizer and so on. And to go even further, you don't have to really theoretically calculate them, you can calibrate for them. So for example, you can obtain the Mueller matrix of your telescope through calibration. And even when we theoretically model the Stokes vector, which we will do in the second part of our course, we are sort of finding this Mueller matrix for the solar atmosphere, because the Stokes vector changes as it travels through medium like magnetized plasma or scattering plasma, etc., and there will be both the modification of my polarization state and some polarized emission on top of that. So let's just talk really briefly in order that you develop some insight here. What kind of physical processes can contribute to the creation of the polarized light? So today we talked, once again today we talked about Hazel, we talked about Hahn effect, scattering polarization and so on. Do you have a feeling what Stokes components would be non-zero when we look at solar prominences, for example, without any magnetic field being involved? So solar prominences, we see them because they scatter light, right? At least in the optical. Their emission is very, very low, like direct emission, thermal emission. What they do is basically they scatter the light coming from the photosphere. In the scattering processes, and this is basically almost 90 degrees scattering, right? Because whenever, so now imagine that I'm looking at this point here, whenever the photon comes from, it scatters toward us, right? So these are all scattering angles are flat. Okay, they're not exactly 90 degrees, but they're close to 90 degrees. Okay. And in 90 degrees scattering, we know from the continuity of electric field that only one component will survive, right? So if here they're plotting it as unpolarized, but forget it. We know now that unpolarized is much more complicated. But if I have both X and Y, when it scatters toward us here, only the y is going to survive. In this direction, only the x is going to survive. Okay. But now comes another, so in principle, because of this, the light coming from the prominence is going to be linearly polarized. And if I define, for example, in this case, if I define my Q being positive and it oscillates vertically, this would be positive Q, right? This would be negative Q. Okay. So now when we look at the prominence, actually when you look at it, you will exactly see that. In the absence of the magnetic field, you will see light which is almost polarized dominantly either, it's either, there's either more electric field along this direction or along this perpendicular direction here. But it's never, not even close to 100%. It's few percent at most. Why? What would you say? There are multiple reasons, but the most obvious one, purely geometric. I tricked you a little bit.
We're looking through a thick layer, basically.
Oh, well, yes and no, but okay, go on.
We'll see the. I mean, that was pretty much it. I don't want to say anything else, but we'll see. Like,
you're right. When we look through very thick regions, there can be so-called multiple scattering, which can destroy polarization. But this is now much more simple.
It's very close to the surface of the sun, so actually the light's coming from, it's not like just coming from below, it's coming from all directions.
Very good. So if you were very far away from the sun, like for example is the Earth's atmosphere, basically when you, theoretically, when you look at the Earth's atmosphere, so that you're looking at light which is really scattered at 90 degrees, you should see 100 polarized light. Of course, it's never like that because it's me scattering which never can produce 100 polarized light and so on and so on. But what you see here is that this point that emits is only few arc seconds above the limb. So the light is coming from many directions. So what's going to happen when light is coming from many directions is it's going to produce, the scattered light is going to have many different orientations. But still, since it's not coming from all the directions, it doesn't exactly calculate, but there is one dominant direction. So when we talk about scattering polarization in like a couple of weeks, I will show you exactly an integral which allows you to relatively simply evaluate the maximum degree of polarization you can get here. Another reason is that spectral lines, when they scatter, they are not usually 100% polarizable, so you can't reach them. There is completely different physics involved in this example here. So when we look at the sunspots from the top, what do we see? Like in the cores of the sunspots, to make things even more simple, in the umbra. What kind of polarization would you expect?
Circular.
Circular, yes. I mean, obviously, if this was linear, it needs to be circular, yeah. And it's circular now because of a completely different effect. So the magnetic fields that we see in the sunspots are strong enough to split the energy levels. And now the energy levels, and here I'm plotting just the most simple case. They consist of these, as I like to call them, Zeeman sublevels. And these are basically different M numbers, if you remember from quantum mechanics. Like you first had different principal quantum number N, then within one principal quantum number you have different angular quantum numbers, different orbital quantum numbers, different L's, and then these are sort of split. These are little split. Like they have different energies and we see different lines corresponding to different L's. But then one L splits into more sublevels, which are generally degenerate, but the magnetic field can break them. And the trick there is, and I will talk about this much further later, is that these, and I'm only mentioning them because of the following thing. Now we're looking at the quantum picture, and these different subtransitions produce different photons. And now when I'm looking at individual photons are always 100% polarized. And their polarization, whether it's circular or linear, just depends on my coordinate system. So it turns out that when I'm looking along the magnetic field, appropriate coordinate system for that to do is to have photons which are positively or negatively circularly polarized. In the absence of the magnetic field, their energies would be exactly the same and their polarizations would cancel. But now, since their energies are shifted, one line is emitting, one subline is emitting toward the red, the other one is emitting toward the blue. Their polarization doesn't cancel and produces this asymmetric signal that we will use to measure the magnetic field. And if you look perpendicularly, now the natural representation is to make them as linearly polarized photons, where these two are negatively polarized, this one is positively polarized. This one, which belongs to the central transition, is unperturbed, it stays at the same energy. The other two are shifted to blue and red, so I get this kind of shape here. And we can measure this, and from this we can directly estimate the magnetic fields, as ones of you who managed to do the full exercise today figured out. Okay, so this was it for today. Just to show you what Stokes parameters are, how we measure them. We didn't talk about the instruments, we didn't talk a lot about modulation and so on and so on. On Thursday, Valentin Martinez-Pilet will give us a talk about, I always make fun, and I ask him, you have to finally explain us what's the difference between the polarimetric sensitivity and precision. So he will hopefully tell us much more than that. And then I will also send the link to people online on Friday. We had a talk by our guest Francisco Iglesias, who will tell us also something about polarization. So you might want to listen to that on Zoom, which should complement this to some degree. Questions, comments, phenomena that are unexplained, and so on and so on. So if you have to remember one thing from today is that Stokes parameters for ideal wave are always such that the wave is completely polarized, but then what we see is the average of many ones with completely different Stokes parameters, and we can only detect, what we see are some small imbalances because of the physical processes. And if there was no scattering, no Zeeman effect, no nothing, QU and V would always be zero. Because we always measure huge amounts of wave packets. We never look at one individual electromagnetic harmonic plane wave. Okay, you all must be exhausted now. So yeah, let's finish today with this. Let's use this opportunity to discuss a little bit further. You can ask Andres about the workshop that we had this morning, and yeah. So yeah, any questions from people online? Okay, I will correct the slides with proper vector notation, and I will put them online as well as the video, and see you all on Thursday.